Welcome to this lecture on survey sampling and Indian official statistics. Today, we are going to explore simple random sampling, which is the absolute bedrock of all statistical surveys and data collection. If you have ever wondered how we can accurately predict the outcome of a massive national election by asking just a few thousand people, you are in the right place. Let us dive in and uncover the math behind it. Now that we know our topic, let us understand what simple random sampling actually is. Imagine drawing names from a well-mixed hat. This method ensures that every single possible group of a given size has the exact same chance of being selected. There are two ways to do this. With replacement means you put the name back, so it could be drawn again. Without replacement means once a name is drawn, it is removed. In the real world, we almost always sample without replacement because there is no benefit to interviewing the exact same person twice. To work with these concepts mathematically, we first need to define our population parameters and sample statistics. The population mean, denoted by a capital Y with a bar over it, is simply the true average of all items in the entire population. Capital N represents the total number of items. Similarly, the sample mean, denoted by a lowercase y with a bar, is the average of just the items we actually selected. Lowercase n represents our sample size. If we increase our sample size n, our sample mean will generally become more stable and get closer to the true population mean. Before we look at the formal mathematical proof, let us see this concept in action with a concrete numerical example. Imagine a tiny population of just 3 students and their test scores are 2, 4 and 6. We want to take a sample of size 2 without replacement. First, we must calculate the true population mean, so we have a clear target to aim for. We add 2, 4 and 6 to get 12 and then divide by our population size of 3. Our true population average is exactly 4. Continuing with our example, we list all possible samples of size 2 we could draw. There are exactly 3 possible pairs. We calculate the sample mean for each pair, giving us 3, 4 and 5. To check if our method is unbiased, we find the expected value by averaging these 3 sample means. Adding them gives 12 divided by 3, which equals 4. This perfectly matches our true population mean, showing physically what unbiasedness means. Now that we have seen it work perfectly in a small example, let us prove mathematically that the sample mean is always unbiased for any population. We start by introducing an indicator variable called a AI, which acts like a simple mathematical switch. It equals 1 if a specific item is selected for our sample and 0 if it is not. The expected value of any random variable is found by multiplying each possible outcome by its probability. The 0 term vanishes completely, leaving just the probability of selection. Since every item has an equal chance, this probability is simply the sample size divided by the population size, or n over capital N. Continuing our proof, we rewrite the sample mean formula using our clever indicator variable. Instead of summing only over the sampled items, we sum over the entire population, letting the indicator variable cancel out the unselected items with a 0. We then apply the expectation operator to both sides. Since the population values are fixed constants, the expectation only affects the random indicator variable. We substitute n over n for the expected value. The sample size n in the numerator and denominator cancel out perfectly, leaving us with the exact mathematical definition of the population mean. We have successfully proven that the sample mean is perfectly unbiased. So we have proven that the sample mean hits the target on average. This brings us to variance. While the sample mean is unbiased, any single sample will not perfectly match the population mean. Variance measures how much our sample estimates fluctuate around the true value. A smaller variance means our estimate is highly precise. To calculate this, we rely on the population mean square, which measures the true spread of the data. Here are the mathematical formulas for the variance of the sample mean. For sampling without replacement, the variance includes a special fraction called the finite population correction factor. As your sample size n increases and gets closer to the total population n, this correction factor shrinks, driving the overall variance down to 0. Now, look at the variance for sampling with replacement. The numerator uses n-1 instead of n-n. Because items are put back into the pool, the variance does not shrink as rapidly when we take larger samples, making it a less efficient method. Let us prove mathematically why statisticians almost always prefer sampling without replacement in the real world. We will compare the two variance formulas side by subtracting the without replacement variance from the with replacement variance. If the final result is positive, it means the with replacement variance is larger and therefore less precise. Since both fractions share the exact same denominator of n times n, we can easily combine them into a single expression. We simply write the two numerators over the common denominator, keeping the population mean square factored out to the side for clarity. This setup makes the algebra much easier to handle in the next step. Continuing the algebra, we simplify the numerator of our combined fraction. The positive population size n and the negative n cancel each other out perfectly. The negative sign then distributes to the negative sample size n, making it positive. This leaves us with a clean numerator of n-1. Because the sample size is always 1 or greater and the population mean square is always positive, this entire difference is always greater than or equal to 0. This proves conclusively that sampling without replacement always gives a smaller variance, providing a more precise and reliable estimate. There is simply no mathematical advantage to putting items back. The variance formulas we just saw are theoretically perfect, but they lead us to a practical problem. They require us to know the true spread of the entire population. In real-world surveys, we do not have that information. Therefore, we must estimate the population variance using only the data we collected in our small sample. By calculating the sample variance, we can determine our margin of error using nothing but the data we actually collected. To estimate the population variance, we first calculate the sample variance, denoted by a lowercase s squared. Notice carefully that we divide by n-1 instead of just n. This crucial adjustment ensures our estimate of the variance is perfectly unbiased. Once we have calculated this sample variance, we plug it directly into our previous variance formula in place of the unknown population value. The little hat symbol over the V indicates that this is an estimated variance, not the exact theoretical variance. By using this, we can calculate the margin of error for our survey. Let us apply this to a realistic scenario. Suppose a factory produces 1,000 batteries. We test a random sample of 5 batteries without replacement, finding lifespans of 10, 12, 15, 11, and 12 hours. We need to estimate the variance of our sample mean. First, we calculate the mean of our sample by adding the lifespans to get 60 and dividing by 5. Our sample mean lifespan is 12 hours. Next, we estimate the population variance using our sample data. We subtract our sample mean of 12 from each data point, square the results, and sum them up. The squared differences are 4, 0, 9, 1, and 0. Adding these gives a total sum of squares equal to 14. To find the sample variance, we divide this sum by the sample size minus 1, which is 4. This gives us a sample variance of 3.5. Finally, we plug our sample variance into the estimated variance formula for sampling without replacement. We use our population size of 1,000 and sample size of 5. Subtracting 5 from 1000 gives 995 in the numerator, and multiplying the denominator gives 5000. Dividing these gives 0.199. Multiplying by our sample variance yields an estimated variance of 0.6965 square hours. Let us visualize what we have been calculating. On the left, you see the large population, representing all n items. The arrows represent the sampling process, pulling a few items into the smaller sample circle on the right. The crucial detail here is the label on the arrows, equal probability. This mathematical fairness is what allows us to calculate exact margins of error and confidently make decisions that affect millions of people. We have covered a lot of ground today. Remember that simple random sampling is the foundation of all surveys because it eliminates human bias. We proved that the sample mean hits the true population target on average. We also saw that sampling without replacement is always better because it yields a smaller variance. Finally, we learned how to estimate that variance using only the data we collected. Excellent work following along with these proofs.